Our new lesson is talking about conservation of energy. In this lesson, we will see what is the law of conservation of energy. The law of conservation of energy is a law of science that states that energy cannot be created or destroyed, but only changed from one form into another form or transferred from one object to another. So the law of conservation, that's there's no energy losses, there's no added energy to the system. Only the energy here, it only transfer from mechanical to heat as an example, or it will be changed from one energy like mechanical to chemical. So it could be transferred from one object to another or changed from one form to another only, but it cannot be created or destroyed. It cannot be, there's no energy added. And I mean, like, if you have like these examples here. In the first example, we have a light. This is um this is a type of energy. Now, this light now, or this energy now, when it's enter the, or it can be converted to a plants, it makes a chemical process. So here inside this system here, this is the light. It's enter, oh, there's a light. It's gonna to the chemical. Now it's gonna convert it to be a chemical. Now, if it is 3 joule as an example, it's converted and stay 3 joule. Without any loss, it will not be 2 joule. 2 joules it will not be 4 joules. It will not be created or destroyed. It's only converted to another type of energy, like chemical one. Here, in this one, there's an electrical energy. You have this electrical fan, you put it on the plug of the wall. Now here you have an electrical energy. This electrical energy is convert, or it's make the pan to start working. When it start working, there's a thermal process it's happen inside it. There's a oven, it's make a stream, it's heats the water inside the pan or the food inside the pan. So there's a thermal process. So here the electrical energy now is converted to a thermal. The same electrical enter is the same thermal energy was entered to the pan. And the same in was the same out. Here, this is on ice cream. Well, this is maybe eat it. Maybe here when he eats something, when you eat an ice cream, there's a chemical, you have a chemical energy that you will use it to ride the bike. And here there's a chemical food, the chemical petrol. Oh yeah, and there's a chemical process that's happened inside the gas station. This chemical process, when it's give you a petrol, give it to the car a petrol, it's make the car to start, it's make it to move, to make its machine, its mechanical energy. So these are an examples of how the energy be converted from one form to another. But there's the form cannot be destroyed, cannot be added, cannot be, there's any loss in the energy. The same energy come in is the same energy come out. Here we have the same examples, but here I want you to know that what you put in is what you get out. You put in 5 joules as a chemical, you have 5 joules to be put out as an electrical. You put in 6 joules as a chemical. So yeah, I mean here you have a car. What did I mean? I mean, like here in this car. And this car is in a closed system here. Now, since we have, oh, I give a chemical energy to the car. What is the type of energy that I add, that I put it in the car? Did I put an electrical or did I put a mechanical? No, I put a chemical. Now, this chemical energy inside the car, it's makes some process, it's converted to be as a mechanical. So the system, it's like this. Imagine now you have a machine here. You put one carrot and this one carrot inside the chopper. It will cut into small pieces. So what did you have here? What did you put? You put a carrot. What did you have? You have a piece. Oh, it's many small, tiny pieces of carrot. So what did you put in? What did you get out? You put a carrot, you will get a carrot. You didn't put an apple and you get a carrot. Now the carrot is converted to a tiny or a small pieces because there's a machine. So inside the machine here, there's a process that's happened that's cut the carrots into a small pieces. It's a closed system. Why? It's closed because the same amount of carrot I put is the same amount of carrot I have. You don't have, you don't put one carrot, but the amount of tiny pieces is for two carrots. What you put, what you get out. Here we have the same in energy. Here you have a motion. This is, oh, you have a bicycle, sorry. For this bicycle here, there's a system. What did you have for this bicycle? You have a chemical energy. There's a chemical energy, it's entered to this closed system. Now, inside his body, there's a chemical thing, chemical things, it's a chemical process that's happened to him. Give him an energy to move. This energy to move, it's come as a mechanical energy now. So he has now an energy to move. So the energy here is conserved. What did you put? What did you get out? That's why sometimes when you eat some foods, you don't have an energy to do anything. Like why? Because some foods, it's mean that you take only 1 joule of energy. This 1 joule of energy inside your body, it will convert it to be a mechanical energy. This mechanical energy of 1 joule that you have now, it's not enough to do anything today. And as an example also for the for the car, if you put 2 liters only in the car as an example, so this chemical process that will happen in the car, it's converted to an mechanical, it's let the car to move, but with less distance than if you put 10 liters. And so on. This is how the energy is conserved. What you put in, what you get out. Let's have some practical applications here for the conservation of energy. The first one, Kelly ran across the room and bumped into her brother, pushing him to the floor. Look at this example here. When you think about it, you don't know what is the relation between physics and this example that's happened in our real life. Yes, there's a relation. The kinetic energy she has, now the girl, she has a kinetic energy because she's moving, she's running across the room. Now, when she bumped into her brother, so here, let's draw it here now. This is a girl, and this is her brother. So a girl is a system, and the brother here is a system. Now, when the girl come and pop pump her brother, so he give him a kinetic energy. This kinetic energy, it is inside his body. Let him to move. So it didn't make anything. It's also come out as a mechanical energy. So the girl give the brother a mechanical energy or the kinetic energy because he's moving. It's let him also to move. So she put a kinetic and the output here is also kinetic. So if you want to draw it here, you have to say that the input is kinetic and the output will be kinetic. When she pump him a little, he will move a little. But when she come and push him with a strong power, he will move with a long distance. This is one example. Let's take another example.
Like you mean here the law of conservation in this example, that because if it push him like with a great energy, he will go like far away, more far away, right?
Yeah.
So they both have a law of conservation.
So what you get, or what do you put, what you get. This is the meaning of conservation of energy. Look at the example number 2 now. Sam was rearranging furniture and needed help to push the heavy sofa. His brother came over, and together they were able to lift the sofa onto the sliders. This is made it easy to push the sofa across the room. When Sam and his brother pushed the sofa and slid it across the wood floor, energy was transformed from the man to the piece of furniture. So this is now this is real example, real practical example that's happened in our life. I have a furniture, I have a piece of sofa. I want now to push it, to rearrange it, I want to rearrange my room. I want to push the sofa to the right. When I try now to apply a force on it, I have an energy, but this applying, and I have this is not the sofa here. This is not a sofa, this is a car. Now this is a sofa. So when he was here, or when Sam started to move it, he applied a force on it. A force with a distance. He has a work, or the work, in other words, during a time, it's an energy. Now, this energy now, he apply a kinetic energy on the sofa, but this energy is not enough to let the sofa moving. He asked his brother to come and help him. When his brother come, so you have now more energy to what? To push the car, to push the sofa. When you have more energy, this one, it's led the sofa to move. So it's make the sofa now to move, it start moving. So they put this in this system here, in the system of the sofa, we have they put a kinetic energy, and since it start moving, so we have a kinetic energy that's go outside. Another example. When a moving car hits a parked car and causes the parked car to move. So here you have your car. And you have here another car. But your car is moving on a street. Now, when you are moving on the street, You have a kinetic energy because a kinetic is energy of moving, energy of motion. So when you are moving, you are driving your car. Since we hit the car that is at rest, the car before hitting it, there's no energy in it. But since now you hit the car, you give here, or you give it a kinetic energy. This kinetic energy, it lets the car to move. So kinetic energy in, kinetic energy out. When you hit it, lets the car move. Another example, when you push a book across the table, the energy from your moving arm is transferred from your body to the book, causing the book to move. When you read these examples, you say that it is okay. We know it. No, we know that will happen, but you don't know why. You know that if you push the book will move. But why? You know that if you hit the car will move. You know that if you want to push the bicycle as an example, or the book or anything, or the chair will move. But why? This is, we know it by default, but now we know why. Because there's an energy, you apply it to the book. From where this energy? I have my energy in my hand, in my arm. I have a kinetic energy because I move my arm. This kinetic energy, it's entered to the book and it's the book to move. So the kinetic energy in, the kinetic energy out. Here also the same examples. When the car hit the road sign, the sign fell over. You know that you are in the car here now. Here you have a road sign. Now, when the car hit the road sign, the sign fell over. Why? Because the energy was transferred from the moving car to the sign. Let's the sign to move. Another example. Two football players collided on the field, and the both went flying backwards. Energy was transferred to each player, sending them to the opposite direction from which they have been running. Here we have two football players that they are collided. Now, because of momentum, we know that when they are collided both of them are going to the opposite side because of momentum. We know why they are going to the opposite side, but why they are moving? Because of the energy. The energy that's the first man give to the second man, let him to the move to the right, and the second man give the energy to the first man, let him move to the left. This is also an example of energy. Do you have another example, or can you think of other examples? Okay, so do you have any question here?
No, it's clear.
No, for me it's clear.
Okay.
Like when you push like a ball, like there is a ball and this ball have a potential energy and you two have a potential energy. But then when you move, you will have a kinetic energy. And when you push it, then you will have a law of conservation. Like the more you push it, the more it will go far away.
Yeah, so you put a kinetic and the car will be moved. Well, it's not
I'm
only
thinking
kinetic.
in nuclear reactors also.
Sorry?
In nuclear reactors, the nuclear energy is converted to electrical energy for cities.
Yeah, and here these examples are for mechanical. Here it's all concentrated on mechanical energy. But if you come back here we have other types of energy, like mechanical, chemical, electrical, radical, and so on. or not sorry, radiant. So, or
What
thermal.
I said, mechanical, right? For mine, it was mechanical before.
Yeah. Well, no, for all of these examples are mechanical. But these examples, it could be electrical, thermal, what also? Chemical,
Like they are all
mechanical,
kind of
thermal,
chemical energy.
nuclear, what?
Like they are chemical energy, not mechanical energy.
Yeah. So yeah, I give you some examples, but we are going here to talk about mechanical. Now let's see this example here.
Oh
Now
yeah,
let's
teacher,
see
are we
now.
going to make the non-mechanical energy?
No.
Okay.
Now here now we have. Let's see now what is the meaning of conservation. Yani, I mean like in math or in numbers. What's the meaning of conservation? I told you that you put 10, you have 10. You put 9, you have 9. So what will happen here if there's a ball and this ball now starts moving from, oh, the ball is throwing down from a place. Here, there's a ball. And this ball now is, this is the ball here. Let's make it bigger. This is the ball, okay? This is the purple ball. Now this ball is at height of 10 meters. It's at rest. It didn't move. So since it's at rest, there's a potential energy, but there's no kinetic energy. So let's now find here the potential energy at this height here. Now, at this height here, the potential energy, we said before that the potential energy is mgh, and the kinetic energy is half mv squared. So the potential energy at this point here is the mass times g times h. Now assume the mass is 1, the g is 9.8, and the height here. Now let's see now where's the ball. The ball has a height of 10 meters. So
it is 10
times 10. So the potential energy will be 98 joules. What about the kinetic now? The kinetic is half
it will be 0
mv squared. Half times 0 times the 1. Now where's the velocity? It's not moving.
It's 0 because it's not moving.
So the velocity here is 0. So because of that, the kinetic energy will be 0. So at this point here, when it is at 10 meters, the potential energy is 98 joule and the kinetic is 0. So what is the summation here, or what is the total energy here?
It's 98.
It's 98. So after now we solve it here. So let's find that the total energy at this point at 10 meters is 98 plus 0, which is, we can write it as potential energy. Every time the total energy is potential energy plus kinetic energy. 98.
You mean like the mechanical energy, right?
Potential plus kinetic. Yes. It will be 98 joules. Let's now have it here at 8 meter. At 8 meter, the potential energy is M1 times G 9.8 times H,
which is
what
8.
is the height now? It is 8. So when you multiply it here, you get the answer as
73.4.
شو هاي؟ تذكر قاري صح؟
No, I'm sorry. Back. Now 9.8 times 8. Let's multiply it now on the calculator here. It is 78.4. So it's not at 8. He find the potential energy here at maybe 7.5. Let's try 7.5. So this number here, what's happened? Let's try now 9.8 times 7.5, which is 73.5. So here at 7.5, the potential energy will be 73.5. Now let's find now the kinetic energy. The kinetic energy half mv squared. So half v squared is ke. So let's first imagine now that's the velocity here is 7. So the velocity here is 7 meters per second squared. So 7 squared times half would be the kinetic energy, which is 24.5 joule. So at 7.5 meter, after 2.5 meter, there's a potential and there's a kinetic, because the ball it still have a potential energy, but the potential energy now at the beginning it was 98, but after 2.5 meters it is 73.5 joules. So that's mean the potential energy now will be decreased since it's going down, but the kinetic energy it starts with 0, but now it's come as 24.5. It starts to increase. Now now look at the total of them.
The total will be 98 because
73.5. If you add it to 24.5, you will have the total energy as so the total energy here it was 98 joules. Now let's see now at this point here and at this point here. Let's find it now at 5.5, inshallah. So the potential energy here is half times 9.8 times 5.5. No, it's not at 5. المهم هلا so what did I mean? I mean that I don't know the numbers that I tried to suggest some numbers for you, but the most important for me now, when the ball is at 10 meter, the potential energy is 98. At 8 meter, it is 73.5. At 6 meter, it's 49. At 2 meters, it's 24.5. So they are decreasing until it will reach the earth, reach the ground. The potential energy now is 0 joule. So the potential, it starts with 98, it will decreasing until it reaches 0. Now look at the ball when the kinetic energy when it's at 10 meter. At 10 meter, the kinetic energy is 0. It starts moving, the kinetic energy increased, it's 24.5. At this point here, it's 49. At this point here, it's 73.5. And at the last point, when it's near the ground, it has 98. Now, after that, how the energy here now is conserved. Here now, as you see, the total energy when it is 10 meter, it is 98. And here it's 98. And here it's 98. And here it's 98. And here it's 98. So that's why the total of the energy here is conserved. The total energy at any point will be the same. Is it clear?
Yeah.
Yes, teacher.
Okay. Now, so by now, we say that the conservation of energy, that means energy cannot be destroyed or created. It's changed from form to form. The forms like mechanical, kinetic, chemical, and so on, into another form. In a closed system, the summation of all forms of energy will be constant. Now, before talking about what is the closed system, let's see what the laws of conservations that we talk by now. We talk about the conservation of linear momentum. We talk about the conservation of mass. We talk about the conservation of energy and the conservation of electrical charge. These are they are five. One, conservation of linear momentum, and there's a conservation of angular momentum. There's a conservation of mass, energy, and electrical charge. These the five laws of conservation in physics. So now let's go talk about what is the closed system. So the term of closed system, that's mean something refers to something where nothing you get on or out. Closed, then you mean like you close the you have a box, you close it. So when you close the box, there's nothing that will be lost and there's nothing will be added. So this is the meaning of closed. So in physics, we say that that's mean the total amount of energy that's come in a system will equal the same amount or the same amount of energy that's come out of the system. So let's have these types of system here. We have three main types of system in physics: open, closed, and isolated. Open system, look at this picture here. It's like you put a heat, and there's a heat also when you get outside. There's a work added, and there's a work will go outside, but there's some matters here escaped. So there's a loss. The loss on the matter, it's mean loss on the heat. Some like this example here. Here, like this is a boiling water without a lid. Here now, the energy now, it has a freely motion, it has freely to move. So that means that the energy it can go outside the system. There's nothing that let him don't move or don't go out of the system. So this is an example of open. You have a boiling water, but without a lid. That's why sometimes when you want to boil a water, if you didn't cover it, close it with a lid, it takes more time. Why it take more time? Because there's a loss on heat, there's a loss of energy. It take a lot of time to make the water start boiling. And sometimes you look at the water, the amount of water, it will be less than you will put it before. Why? Because in the open system, you have some mechanical process. It's like the matter escape from the this container. Yeah. This is the meaning of open system. Now, let's talk about closed. Closed, there's nothing transferred, nothing lost, or nothing added. Heat in, heat out, work in, work out. Some of the example of the closed system, like the pressure cooker, or anything you close it. Here, this doesn't allow any exchange on the meter. What did you put inside the pressure system, the cooker here? What did you have at the ending, at the last, or at that when the time ends? So there's nothing will be transferred. The energy cannot be transferred here. What happened inside the pressure here? The heat is transferred from a stove to the water. Here you have a steam, the stove is give a heat. The heat that enter, it's make the water to start boiling. So the heat now is going to the water and heat it. There's a steam is not allowed to escape. I know you know what is a pressure cooker. If you try it, there's no steam allowed to go outside. So this is the example of a closed. There's nothing happen. There's nothing added or lost if you have a pressure. I'm sorry, if you have a pressure cooker. This is the meaning of closed system. Isolated system, it's didn't like to add anything, or there's nothing will escape from it. It's isolated. The isolated system is like this one here, the thermal flask. This one, there's no heat can transfer from it. If you put a coffee inside it at morning, when you are going now you are going back to home, you will find that the same coffee inside the thermal flask with the same heat that when it's at the morning, because there's no energy losses, there's no heat losses, there's no material losses from this thermal flask. If sometimes you will find it that it is cooler than at the morning because of the material that is manufactured, the material that's used to manufacture this type of flask. It could be, as an example, made in country, China, as an example. It's not used a very effective material that's exactly let it, the objects didn't let it, there's an it's like it's an isolator materials that didn't let the energy